So in our next section, we're going to start our next major topic domain, which is Overlay Transport Virtualization, or OTV. And first thing we want to know, of course, is what is OTV? What's the use case of it? Why is it there as opposed to the other potential options that we have for layer 2 extension? Okay, specifically, it is Overlay Transport Virtualization, which basically is an Ethernet over IP tunnel. Okay, so it's going to be another mechanism similar to virtual extensible LAN that we can take a regular Ethernet payload, put it inside of an IP packet, route it to the other end of the network, remove the Ethernet header, and then bridge the packet to the final destination. Okay, the ultimate use case for this is typically going to be virtual machine workload mobility, or what would more commonly be known as VMware vMotion. Like you have a web server in one data center site, you want to move that virtual machine over to another site, like you're trying to do active data centers, or you're trying to do active standby, like disaster recovery. But in order to do this, we need to span the layer 2 VLAN to make sure that when the virtual machine moves, we don't have to update its IP address, we don't have to update its default gateway, we don't have to update the ARP cache, which implies that we need to extend the layer 2 VLAN between the multiple sites. Okay, you'll see sometimes OTV is referred to as MAC in IP routing because we're making our forwarding decision based on both the Ethernet address, which is going to be the MAC address, and then also based on the IP address, so the regular IPv4 outer header. And you can think of OTV as a site-to-site tunnel, where VXLAN typically we use that as more of kind of a host-to-host tunnel. So think of this loosely analogous to an IPsec site-to-site tunnel versus an IPsec remote access tunnel. This would be like if I have an office in Chicago and I want everyone in the office to be able to VPN to everyone in the office in New York. I could just configure a tunnel between the two edge routers, encrypt all the traffic between them. That's going to be analogous to OTV. Where something like VXLAN is generally going to be for your intra-fabric routing. Like I have host A that wants to get layer 2 reachability to host B. I don't care whether they're in the same data center or potentially if they're in different data centers, because that's going to be kind of a more dynamic host-to-host type application. Ultimately, they're really going to do the same thing at the end of the day, which is to extend layer 2 Ethernet across an IP network. But there's specific use cases as to why you would choose to implement OTV as opposed to other technologies, which is mainly what we're going to be focusing on in this section. Why would you want to use OTV to begin with? Okay, so like I mentioned, main use case is going to be virtual machine workload mobility, okay, like vMotion. But when we look at OTV versus other potential solutions, the first advantage of this is that it is transport agnostic. Or basically what this means is that it doesn't care if you're riding over MPLS, if you're riding over dark fiber between the sites, technically could be just regular internet transport. The only real requirement for OTV is that you can ping between the two endpoints, like you have regular IPv4 reachability, and then we can take Ethernet, put it inside IP, route the packet to the remote end, and then remove the Ethernet header out of it. Okay, we'll see besides using the regular hardware platforms that we're looking at today, like the Nexus 7Ks, you can also run OTV on Cisco's virtual router, which is the Cloud Services Router 1000V or the CSR 1000V. Use case for this would be that if I have virtual machines in my Chicago data center, but then I also want to extend layer 2 into the cloud, like Amazon EC2, Rackspace, something like that, you could run CSR 1000V as a virtual machine inside the cloud, and then you could connect to it across an OTV tunnel to your physical hardware box. Okay, so hardware box could be like a Nexus 7K on my end, virtual box being in the other end in the cloud. Hardware box could also be like an ASR 1000, okay, ASR 1000X, and then basically doing the layer 2 extension between the different endpoints. Okay, beyond this in terms of the transport, the other main thing we'll see is that there's a bunch of enhancements that are inherent to OTV as we compare it to the other layer 2 tunneling techniques. Okay, so let's say, for example, that we had two data center sites and we just plug them in physically with a dark fiber. Okay, like you have a single mode fiber on your Chicago data center side, you have one on your New York side, and then the routers at the edge, you have them configured in the same subnet. You're basically just expanding layer 2 between the sites. Now, if we were to, or excuse me, not the routers, if you were to do this with layer 2 switching, Okay, so you just plug your regular Ethernet switch on one end, you plug your Ethernet switch on the other end, and then they're going to be directly attached over a layer 2 trunk link. One of the big disadvantages of this traditionally is that anytime you're expanding spanning tree, okay, or extending spanning tree, you have the potential for a larger failure domain. Okay, like if one of the links goes down or one of the nodes goes down in your Chicago data center, you don't want everyone in the New York data center to have to reconverge the layer 2 topology, which in the case of spanning tree would be flushing out all the MAC addresses, potentially doing a new root bridge election, potentially dropping traffic while you're in the process of reconverging. One of the other optimizations is that when you have your hosts in data center A that are ARPing for destinations in data center B, instead of taking that Ethernet broadcast frame and sending it all the way across the data center interconnect and then waiting for their ARP response to come in from the remote server, OTV is going to have a caching mechanism built in that is basically snooping inside of the layer 2 payload, looking for ARP frames, and then it's going to cache whatever the IP to MAC address mapping is and reply locally to whatever the resource that's trying to resolve the address. Okay, so let's say, for example, that we have host A in Chicago that is trying to reach host B in New York, and then you have your two routers at the edge. So we have router 1 and we have router 2 that are connected together with the IP network in the middle, and these are the boxes running overlay transport virtualization. So what we would see happen first is that the ARP comes in. The ARP is going to get encapsulated inside of IP. Okay, so it's going to be an Ethernet packet inside of IP. Goes to the other end. This is going to be flooded as a normal Ethernet packet. Okay, so it's going to be going to all Fs from a layer 2 point of view. The ARP request goes down to the final destination. Final destination says, hey, that's me. Okay, I'm going to send back my ARP response. When this response comes in, router 1, who's running the overlay transport virtualization tunnel, it's basically going to keep its own local ARP cache. So then beyond that, if we have host C, D, E, etc., in the Chicago data center, you go to ARP for the destination. You're not going to have to send that all the way across the data center interconnect. So we'll see it has a bunch of optimizations, not only for the address resolution protocol, but also any broadcast unknowns and multicast or bum traffic in general, that it gives you more control as to what type of layer 2 payloads that you're sending across the link, as opposed to something like a dark fiber or an MPLS layer 2 circuit, like a point-to-point pseudo-wire or a virtual private LAN service, which are essentially just going to bridge all traffic transparently. So both the layer 2 control plane, like spanning tree information, plus any of the layer 3 data plane, like your ARPs, your broadcasts, and so on and so forth. Okay, so what OTV would prevent for us is that if you completely hose one of your data centers and you have a broadcast storm, OTV is not going to bridge that across the tunnel. Okay, so there's a bunch of protection mechanisms that are built in. Okay, beyond this, one of the other advantages of running the feature is that it's hardware accelerated. Okay, with hardware acceleration, like we've seen with a lot of other features up to this point, it does mean that it is going to be platform specific. It's also going to be version specific and hardware specific within that individual platform. Okay, like in the case of the Nexus 7Ks, if we were to go to the cisco.com/go/nexus page, and then under data center switches, we're going to go down to products and services. Then under Nexus switches, we're going to go down to Nexus 7K and compare models. And then what we want to look at here is what are the different line cards. Okay, we want the M cards and we want the F cards. Okay, M series IO, F series IO. Okay, under the M cards, there is a row here for overlay transport virtualization. Here there should be. Okay, notice all of these say yes. Okay, so supported on all the M cards from the original M132 all the way up to the current one, which is the 12-port 100 gig card for the Nexus 7700. Okay, also notice here that the fabric bandwidth for this card is 1200 gigabits per second, or in other words, the line card's line rate at layer 3. So if you're doing an OTV tunnel with this 100 gig Ethernet as your data center interconnect, you can hardware accelerate it up to line rate. Okay, whereas opposed to something like ASR 1000 or a virtual router like CSR 1000V, you're not able to hit line rate on the ASR unless you have the specific modules, the specific like port adapters plus the fabric modules in order to get there. But in the case of the Nexus 7K, by design, it is line rate. The limitation, though, is going to be on the F cards. The F1 cards and the F2 or F2E cards, these ones do not support OTV, okay, which is down here. Okay, same is going to be with Lisp, the locator ID separation protocol, and then MPLS. Basically, they're going to go hand in hand. So these first two rows here are F2E, and then everything to the right of here is going to be the F3 card, which is the current generation. Okay, this also means that on the Nexus 5Ks, 6Ks, Nexus 9K, like in the case of ACI, those do not support overlay transport virtualization. Okay, so mainly it's just going to be two overall platforms. So it's going to be Nexus 7K with either the M cards or the F3 line card, okay, or whatever's newer after that, and then the ASR 1000. So either the hardware box like ASR 1KX or the virtual box, which would be CSR 1000V.